Welcome to Math with EJD. In this video, we continue with partial differential equations, and our focus is on the wave equation and the D'Alembert's solution. So far, we've seen different types of solutions. You know, talking about method of characteristics for first order. For second order, we've seen separation of variables method. We've seen how to use Fourier series to solve a partial differential equation. Now, for wave equation, we are focusing on the D'Alembert's solution. Let's see how this goes. Starting with an overview. So wave equation, the wave equation describes the propagation of waves, propagation of waves such as sound waves, light waves, knowing that light has dual nature. It can be a wave, it can be a particle, and even water waves, as evidenced by ripples in a water body, right? And water waves, and okay, and water waves for sure. So in one dimension, the wave equation is typically written as partial squared u of x comma t all over partial t squared equals c squared partial squared u of x comma t all over partial x squared, where u of x comma t is displacement, the displacement of the wave at position x and time t. Then we have c, which is the wave speed, and that is a constant. Of course, it can vary in different media, but it's a constant in a particular, if you are observing it in a particular medium, I believe. So let's go for general solution to the wave equation. So general solution to the wave equation. Since we are focused on D'Alembert, so that'll be the D'Alembert approach to things here. So the general solution to the wave equation in one dimension is given by D'Alembert's formula. D'Alembert's formula, which is given as u of x comma t equals f of x minus ct plus g of x plus ct. This is a general solution according to D'Alembert. So here we have that f of x f of x minus ct actually represents the wave traveling, the wave traveling, the wave traveling to the right, that is positive x direction. So that if you have this, you have the wave going in this direction. the wave going in this direction. So f of x minus ct represent the wave traveling to the right, which is the positive x direction. And then you have g of x plus ct, which represents the wave traveling to the left. Okay, that is the negative x direction. So if this is the geometry, so you have the wave traveling in this opposite direction like this. So the wave is going that way. So so that's the that's the general solution to the wave, right? But then we can apply initial conditions. Apply initial conditions. So to solve the wave equation, to solve the wave equation for a specific problem, we need to apply initial conditions. Typically, two initial conditions are given. For a wave equation, I think we've done one, even when we did the separation of variables, right? We always have two initial conditions for wave. And the first one is the initial displacement. Initial displacement. So at time zero, right? What was the displacement like? That's u x comma 0, which is phi of x. So that's the initial displacement. And we also have the initial velocity. Because we have a speed as the wave is traveling, right? So initial velocity, which is partial u of x comma t, partial t, evaluated at time t equals 0, and that is psi x, okay? That's a derivative of the initial displacement. So let's use these conditions to find the specific, I want to find the specific form of f and g. We already know f and g are functions of x minus ct and x plus ct respectively. So when we solve using the Limbat solution, we actually want to see how exactly what the f and g look like actually. So let's look at the step-by-step solution, step-by-step solution. So first of all, talking about initial displacement. So since we are talking about applying initial condition, so initial displacement. So we are given that u of x comma 0 equals phi of x, just like we saw up there. So if we substituting, of course, what this simply means is that when t is equal to 0, u at any value of x is phi of x. So phi of x is what describes u for at the initial time. So substituting t equals 0 into the general solution, Of course, we know what the general solution looks like. It's that u of x comma t is equal to f of what's that now? F of x minus ct plus g of x plus ct. So if we substitute this now, so it means that when t is 0, we have this whole expression to be phi of x. So, okay, let me say u of x comma 0 implies that t equals 0 implies that u of x comma t is equal to phi over x. So in essence, we are saying that this we are saying that u of x comma 0 now is simply f of, because t is 0, so we have f of x plus g of x, and all of that will just be equal to phi of x, basically. All right, so this is the expression. So we have this part that f of x plus g of x is simply equal to phi of x. So that's for initial displacement. What if we talk about initial velocity? Initial velocity. So for initial velocity, okay, let me follow the same pattern. So for initial velocity, so the velocity is the time derivative, of u of x comma t. So that simply means that when we have u of x t equals f of x minus ct plus g of x plus ct, so that simply means that partial u of x comma t partial t is the time derivative. So we are focusing on time now. So when we differentiate this with respect to t, so differentiate inside, you have x minus ct with respect to t. So we have minus c f prime of x minus ct. And when we come here, differentiate with respect to t, we have plus c g prime x plus ct. Okay, so we have that. So the condition, right? So the condition, you remember this, the initial displacement thing, okay, is psi x. So partial u of x comma t partial t evaluated at t equals 0 equals psi of x simply implies that when t is equal to t equals 0 simply means that when we put all of this expression here, so when t is 0, then du of x comma t dt is simply psi of x. So if we substitute that into this expression, so we have du of x comma 0 dt implies that, just like this also implies, right? Just as this also implies. So this implies that when you put t equals 0, so that means you have minus c f prime of x, okay? Because t is 0, minus c f prime of x plus c g prime of x. And all of this is equal to psi of x. So we have this again in that situation. So, this will lead to the fact that if we tidy things up, right? Mm, say we divide through by c. So if we divide through by c, we have minus f prime of x plus g prime of x equals psi of x all over c, which is exactly the same thing as, okay. So that would be exactly the same thing as g prime of x minus f prime of x equals psi of x all over c. So we have this expression, or we can even leave it the way it is up there, we can leave it the way it is up there for easy handling later. So let's just leave it the way it is here, because now we have two expressions. We have f of x plus g of x is equal to phi of x. So have I been listing steps? Okay. I think to make things easier, right? Let's just say this is step one, and this is step two. Okay, so other numberings will not confuse us. Then we go for step three. So in step three now, we solve for f of x and g of x based on what we already have. So now we have two equations. So since we have two equations, right, that will be f of x plus g of x equals phi of x. As we see, that's from here. Then the other one is this one we have now. Okay, that's minus f prime of x plus g prime of x equals psi of x over c. So that's minus f prime of x plus g prime of x, okay, equals psi of x all over c. So we have these two equations. So what we can then do is we can integrate, right? So we have, this is equation one, or let me even label it my own way. Call this equation one and call this equation two. So, you know what we want to do is to solve for f of x and g of x. So one way to handle this is already f of x plus g of x equals phi of x. So one way to handle this second part is to integrate. So we can integrate to, integrating to, we have the integral of minus f prime of x plus g prime of x equals integral of psi of x over c. Okay, so we can tidy that up by having minus integral of f prime of x, okay, all of this dx, f prime of x dx plus integral of g prime of x dx, okay, and that is equal to 1 over c integral of psi of x dx. So of course, we know integral of f prime of x is just f of f prime of x. I mean, integral of f prime of x is f of x. So we have minus f of x plus g of x equals 1 over c integral of psi of x dx. So if that is the case, we can call this equation 3 for sure. We can call this equation 3. So, I mean, it's clear this is positive and this is negative. If we add them together, we can easily get our g, and then we can move on from there. So we can say, if we add equation 1 and equation 2, let me change markers at this point. So equation 1 plus equation 3, rather. Equation 1 plus equation 3 means that we have f of x minus f of x, that's 0. And then we have g of x plus g of x. That gives us 2g of x equals, on the right hand, we are also adding. So this is phi of x plus this integral now. So we have phi of x, okay, plus 1 over c integral of psi of x dx. Okay, so that means g of x is equal to 1 over 2 into phi of x plus 1 over c integral of psi of x dx. So this is our g of x now. So we can also look for g of x, right? So we have added here. So what if we want to subtract? We can also subtract to get g of x. So now we say equation 1 minus equation 3. That will be f of x minus f of x. That's 2f of x. G of x cancels out. So now we say equation 1 minus equation 3. Equation 1 minus equation 3. That will be this is f of x minus minus f of x. That's 2f of x. Then if we say g of x minus g of x, that's 0. And then we can have phi of x minus all that. So we have phi of x minus 1 over c integral of psi of x dx. Okay, so that f of x now is equal to 1 over 2 into phi of x minus 1 over c integral of phi of x dx, like this. So we have f of x now and g of x clearly. So we can then talk about final solution. So that's step 3, right? Step 4 now, final solution. So step 4, final solution. So for final solution, we are saying that the solution to the wave equation, is u of x of t equals f of x minus ct plus g of x plus ct, right? So if that is the case, so substituting the expressions for f of x and g of x will simply give us that u of x comma t is equal to, what is f of x? F of x is this half phi of x. So anywhere you see x, you just put x minus ct, that's all. So f of x is half into phi of x. So for f of, this is the first one, f of x. Or let me write that out first. Let me write that out first. So u of x comma t is f of x minus ct, okay, plus g of x plus ct. So we now have u of x comma t equals f of x minus ct, because f of x is half So we have half into phi of x, now we phi of x minus ct, okay, then minus 1 over c integral of psi of x minus ct, okay, psi of x minus ct dx. That's one side, plus the other side we have, I think the only difference is that minus before 1 over c, right? Yeah, so the other one is now plus. So we just have exactly the same expression with plus. So we now have, if I shrink this is 1 over 2 into phi of x plus ct now plus ct. Now, instead of minus here, we now have plus again, because for g, it's plus, okay? So that's plus 1 over c, shrink it for that, 1 over c integral of psi x plus ct dx. And that is, so this is the final solution using D'Alembert's approach. So we can say that this is the solution. This is the solution to the wave equation. With the given initial conditions. Okay, that's the solution. So based on this, now we can take a worked problem. Let's see that. So let us now go as we have this now. So let's go this example. So consider a string vibrating with the following initial conditions. First of all, we have u of x, comma 0 equals sine pi x, because that is the initial displacement, because that's just u, initial displacement. Then we have partial u of x, comma t, partial t, evaluated at t equals 0 is 0. And that is initial velocity or initial speed. That's initial velocity. Okay. Initial velocity. Okay. So the idea is we need to solve for u of x, comma t. So we go step by step. In step 1, we apply the initial displacement condition, Okay. Of course, the D'Alembert's general solution, D'Alembert general solution is u x comma t is equal to f of x plus, I think it's minus first, right? F of x minus ct plus g of x plus ct. That's the D'Alembert general solution. So with that first initial condition so u of x, comma 0 equals sine pi x, right? Sine pi x simply implies that t is 0 and then u is sine pi x, basically. So if we apply that here, it simply means we have u of x, comma 0 such that, so when we put t for 0 for t, so we just have f of x plus g of x equals sine pi x. So equals sine pi x. So we have this as our equation 1. Okay. Next we have that's initial. So we have this. Then in step 2 now, we now apply the initial velocity. Of course, just like we know, again, u of x comma t is f of x minus ct plus g of x plus ct. So partial u of x comma t partial t is minus c f prime of x minus ct plus c g prime x plus ct. So we have that. So then we can remind ourselves that partial u of x comma t at partial t at t equals 0 simply implies that when t is 0, then partial u of x comma t partial t evaluated at t equals 0 is simply 0. Okay, so if we apply that to this case, so it means that 0 is equal to, so we put t equals 0 also, so we have minus c f prime of x, right? Because t is 0, plus c g prime of x, because t is 0. 0 times c goes. So from here, we can divide through by c. So we have 0 equals, in fact, we can divide through by minus c. So it means that 0 is equal to f prime of x minus g prime of x. Okay. So, and this simply means that f prime of x is equal to g prime of x. So we can integrate both sides. So integrating, so if we integrate now, we have integral of f prime of x dx equals integral of g prime of x dx. So that is f of x equals g of x plus constant c. So this is the relationship we have here now. So now substitute f of x equals g of x plus c into equation 1. If you remember equation 1, it's f of x, when we add the initial displacement, f of x plus g of x equals sine pi x. Okay, so anywhere we see f of x, we put g of x, right? So we have, for f of x now, we have g of x plus c plus g of x equals sine pi x sine pi x. So we have g of x plus c plus g of x equals sine pi x. So that means that 2g of x plus constant c is sine pi x. Okay, so that tells us that 2g of x is equal to sine pi x minus c. So that g of x alone now is equal to 2, okay, into sine, sorry, divided by through by 2. That's 1 over 2, 1 over 2 into sine pi x minus c. So that gives us g of x. Okay, that gives us g of x. Okay. Again, since, so we now need to remind ourselves that since f prime of x is equal to g prime of x, so we find that f of x, it's more like we are dealing with the last result we got, right? So f prime of x is g prime of x. So that means that f prime of x is equal to the derivative of this, right? And if we differentiate that with respect to x, so that's sine pi x minus c plus another c. Okay, I mean, no worries. We just know that since that is the case, we can get f of x to be g of x already. That's half sine pi x, half sine pi x minus c, which you had, plus another c. Okay, so that so with that we can then say we have f of x to be equal to half sine pi x, then minus half c plus c. Everything just goes to constant c, so we don't have to worry. So f of x gets us this. So the final solution now, if I must call that a step, let's say that's step 3. So step 3, where we now have a final solution. That's like final solution. So say the solution is u of x comma t equals, that should be f of x minus ct. Okay, so anywhere we see Anywhere we see x, we put x minus t. Okay. So that means we just have half sine pi into, it should be pi x. So pi x minus t plus sine, half sine pi into x plus t. And that is the final result in that case. So we can then say this is the displacement. This is the displacement of the wave. This is the displacement of the wave at any time, t. Interestingly, I have a Python code to visualize this. So let's see what that looks like. Right here, wave equation and the Lambert. So again, we define our phi, we define our psi, that's sine pi x, and psi is 0, the initial condition. If the wave is 1, and then we have all the f and g defined the way they are, and we run this, so we have something beautiful coming out of this. So this is, you can see how it all goes at different times, starting from time 0 with the blue and so on and so forth. So we have that, the wave like that. So it's more like you're strumming a guitar and it's all going like that. So what if I change the wave to say 10? Let me see. That's going to have a drastic impact on it. So you see, we have the time is lengthier or something. Yeah, we have it's, so the waves become larger or something like that. So what if I make it 100? I know that's a lot. Let's see what impact it has. Okay, something like this. So we have all of that like that. So back to 1, we just have this. All right. So with that in place, that is what the Limbat looks like. Let me see if we can get 1 or 2 practice questions before it's over. Let me see. Okay, I think I like this. Um, practice. Practice. Given, how we want, given the wave equation, phi d squared u dt squared equals c squared d squared u dx squared. Okay, solve for u of x comma t, the displacement, using the following initial conditions. Okay, that's u x0 equals ux0 equals e raised to power minus x squared, then partial u, partial t, evaluated at t, or better still, I can even say partial u, 0, partial u, x equals 0, partial t. You can even say that is sine pi x. So do that, you're going to get some interesting results. Then number 2, let me see which one I pick here. Number 2. Okay, let's do this. Solve the wave equation. Solve the wave equation, partial squared u. Of course, the wave equation is just what it is. The only thing that just changes will be the initial conditions or something. So partial squared u, partial x squared with the following initial condition: u of x comma 0 equals x sine pi x, and then you have partial u x0 partial t is equal to 0. So that 0 will help simplify it. So let me see your answers in the comment section, either on YouTube or on Facebook. And feel free to let me know how helpful these videos have been for you. And if you need me to solve a problem or teach a particular topic, feel free to indicate. I might be able to get around to doing all of that. If you have subscribed to the channel, thank you. If you have not subscribed, please go ahead and do that because there's a lot for you to learn on the channel. I have a whole lot, like going to 700 videos already, and more will still come later. And do not forget to hit the notification bell so you can always get alerted each time a new video is released. And lastly, be sure to like and share so that more people can have access to the great content we have on here. Till I come your way again, keep doing maths right. Bye.